Okay, for our last topic in this lesson on time series analysis, we're going to consider autoregression. And the idea of autoregression is that we compare our time series or signal with a shifted version of itself, and then we try to see the extent to which the shifted version matches the original. So I've drawn up here our time signal, in this case just of a simple sinusoidal oscillation. And then below it, several shifted versions of it, drawn in red. So the first one isn't shifted at all. Then the second one is shifted by a small amount. The third one is shifted by a bit more. And the fourth one is shifted by the most. And what we're now going to do is compare the shifted version with the original to try and see if there is a match. Well, when it's not shifted at all, of course, there is a match. This, this is at a peak when this is at a peak, this is at a trough when this is at a trough. That's obviously going to be the case because it's not been shifted. So it's completely going to match. But when it's shifted along a bit, then when this is at its peak, this is at 0. When this is falling through 0, this is at its peak. When this is rising through 0, this is at its trough. So there's no match at all. These signals don't match. And then we look at this one shifted along even more. Well, in this case, when this is reaching its trough, this is at its peak. When this is at its peak, this is at its trough. So again, it's not matched. In fact, it's the exact opposite. And then lastly, this one that's shifted along the most, here this is reaching its peak, this is reaching its peak, this is reaching its trough, this is reaching its trough. So in this case, there is a match. So we would say that when it's shifted by this amount, we have found, we have found a regularity, the repetition in the data. When it's shifted by this amount, it matches itself again. So that is a repetition or period of repetition in the data. That corresponds to a regularity in the data. Well, in this case of a simple sine wave, it's obvious to us. We can see that we just shifted it along one wavelength, one cycle, and so it matches again. But in general, we might have arbitrary data, but the same principle would apply. We might not be able to see it clearly by eye because the regularity may not be perfect as it is in this case, but if we shift it along and find that there's a pretty good match, or the match is better at this with this shift than with other shifts, then we're finding some kind of period to the data, some time regularity in the data. Now, we wouldn't work just with pictures like this. What we're actually doing is going to treat the original version and the shifted version as defining points. So they are an x and y values. So we would take, say, the original as the x values and then the shifted version as the y values. So and then we'd plot a chart. So in this case, that's the original and this is the shifted one. Well, the x and y values are going to be the same, because it's not shifted at all. So whatever that x value is, this y value is the same. So what we're going to find is just that x equals y. So we're going to get a set of points like that, lying perfectly on a straight line. And we then find the correlation between the points of the shifted and the original. So in this case, the correlation, because they lie exactly on a straight line, they're perfectly correlated. So our correlation coefficient, remember from the lesson on statistics, correlation coefficient in this case equals 1. And so this is why it's called autoregression. We're doing a linear regression of the time series against itself. So it's autoregression. And we're finding the correlation. So this is also known as autocorrelation. That's another word we might use. We're looking at the autocorrelation of the data. Well, when it's not shifted at all, the autocorrelation is perfect and correlation coefficient is 1. But now let's have a look at this one. So in this case, we find that when the x value here is large, this is 0. When this is large, the x value is 0. So if we actually plotted those points, we would find what we would get is actually a circle for this perfect sine wave. The points would lie in a circle. And if we did a regression analysis of that and calculated the correlation coefficient of that, we'd find that the correlation is 0. There's no straight line at all. It's correlation of 0. And then what about this one? Well, in this case, they swing opposite to each other. So when x is low, y is high. When x is high, y is low. So when x is low, y is high. When x is high, y is low, and generally all the way through, x and y will just be the opposite of each other. So we'll again get a straight line. This time it will be downward sloping. And this would have a correlation coefficient of -1. They are anti-correlated, perfectly anti-correlated. And then lastly for this one, well, again we've got peak, peak, trough, trough, peak, peak. So we're going to be back to this situation. X is low, y is low, and x is high, y is high. And again, they're just on a straight line, so back to a correlation coefficient of 1. So what we'd do is plot for all the different possible shifts what the correlation coefficient is. So we would shift our points, calculate the correlation coefficient, and then construct a chart of the shift or lag and the correlation coefficient. And so what we'd find is when it's not shifted at all, correlation is of 1, we said. And let's say we can label this, if that's a whole cycle, so I'll call that just 1. This is it's a half there. So this was in fact shifted by a quarter of a cycle. We said when it's shifted by a quarter of a cycle, the correlation coefficient is 0. This is shifted by half a cycle, the correlation coefficient is -1. And then I shifted it by a whole 1, and the correlation coefficient is back to 1. So what we've got is actually a bit curved between those. So what we would do if we plot the correlation against the lag, we find that when we shift it by 1, we get a peak in the autocorrelation. And then we would say, that is then that peak in the autocorrelation means there is a periodicity of 1, whatever it is, 1 century or what have you, in our data. And again, to repeat, with a sine curve, it's fairly obvious, but with arbitrary data, there might be several different cycles and oscillations in our data, so we might find several different peaks, some stronger than others, because there's a strong regularity and maybe weaker regularities within it. So we'll have a look in a moment at the Rome data and see what we get with that when we do this analysis on it. Okay, just to make this a bit more concrete before we go and look at the Rome data, what we would actually do is we would have a set of data in our time series of at various times the value x of whatever it is we're measuring, the amount of war in the world system, the real wages, the area of the empire, whatever it is. And I put here for the time in years 0, 25, 50. That's in the case of the Rome data. It's sampled every 25 years. But whatever it is, it might be every year. Whatever the time axis is here, we've got these values at different times. And then what we would do is we just have this in a spreadsheet or something, and we just put in this column x of t plus 1. So these values have all gone up there. This is x at time t down here, and this is x at time t plus 1, and then this is x at time t plus 2. So these have been shifted up again. And so we do that for all different lags as just as much data as we've got, and we then just plot xt plus 1 against xt, calculate the correlation coefficient, do the straight line fitting, calculate the correlation coefficient, and then do the same for t plus 2. Read again, get some points, calculate the best straight line fit for t plus 2, and then t plus 3, and so on. And then we're going to plot the shifts, so 0, 1, 2, 3, 4, and the correlation coefficient, so we calculate from plotting the data against the lagged or shifted version of the data. So we'll calculate all these R's, and then we're just going to plot, as I was saying before, R against the lag, which will be 1, 2, 3, 4 for all the different columns. Or you don't need to have all the columns, of course. You could just have some other variable that is the amount of lag that goes that tells you what to put in the squares down here. So that's the mechanics of doing autoregression. And now let's have a look at what the picture looks like for the Rome data. Okay, so this is the Rome disturbances. Autocorrelation. And as ever, if it's not shifted at all, we find a perfect correlation. But then there is a peak in the autoregression at 50 years. And there's another peak here at 350 years. And there's also a bit of a peak at 100 years. And then at other values, there's very little correlation or even negative correlation. So these are the key peaks. And we saw in our first Fourier analysis, the 50-year and it was actually 340 years, not 350. But we found those two frequencies within the oscillations in disturbances. And the reason it's 350 years rather than 340 years here is because the data points are every 25 years. That is in Sorokin's data. He put a count of the number of civil disturbances in each 25-year period. So the points are 25 years apart. So we can only shift it by a whole number of points. So it has to be a multiple of 25. But we find that there is, close to that 340 when we shift it by 14 points. In fact, would be a lag of at every 25 years, we find that there is this peak. It autocorrelates with itself at that point. So that is our 340, 350 year cycle. And the 100-year cycle wasn't so obvious in the Fourier analysis, but it came out in the wavelet analysis. We saw that it's only for sort of a period in the middle that this 100-year cycle appears, at a time when the 50-year cycle weakens. But in the autoregression, they both come out here. And that's it. So that's an example of doing autoregression and how it can help you, again, find these periodicities in the data. And now, lastly, I'm going to talk about the association of autoregression with critical slowing down. Now, we talked about critical slowing down in the lesson on critical behavior, and you should recall that it occurs when we're at a stable point, but this is getting close to a critical transition where the stable point is going to disappear. This is shifting up, and when that goes above the axis, this stable point, there will be no intersection, it will disappear. And when we're getting close to that situation, the slope through the fixed point is very shallow, which means that its tendency to move back towards the fixed point operates very slowly, because the rate at which it moves is proportional to, because remember on the charts, in this direction it shows x dot, the rate of change, if that's x. So that's a tendency to move back. So here it's in the positive direction, so it is moving back towards the stable fixed point, but very slowly because x dot is quite small. And similarly here, x dot is small above, but in the negative direction. So it slowly moves back towards it. So that is critical slowing down. When the system is disturbed away from the equilibrium point, the stable point, it will move back towards it very slowly. And if that is the case, it means that if we plot the behavior of the system over time, we will find an increase in autocorrelation. So if you've got data points of where the system is, whatever it is that we're measuring, real wages or wars or area of the empire, we'll find that it returns to some equilibrium very slowly. Therefore, if it was returning quickly, it would, whatever it is now, it would have rapidly, changed a short time later, because it's rapidly moving back towards the equilibrium point. But because it's moving very slowly, even after we lag it a bit, it's still quite close to where it happened to be earlier. It takes a long time to come back away from it. So we'd find that for small lags, there's still a high degree of autocorrelation. So one way to detect critical slowing down is to have the data on the state of the system and do an autoregression on it by small lags, and you'll find an increase in the autocorrelation. Now, another effect that has also is that it increases the variance. So let me just put that increase in autocorrelation. Okay, so I've just written that up. So there's, with critical slowing down, there's an increase in autocorrelation because the system tends to linger and only slowly move back towards the equilibrium. It lingers in whatever state it has been disturbed to. So the shifted values tend still to be quite close to the original. It hasn't sort of snapped back to its equilibrium point. But what I was just going to say as well is it also causes an increase in the variance in the data. Because if the system is not at a critical point and therefore returns quickly to its equilibrium, it will spend most of its time around the fixed point. So if we look at the values of x, they will mostly be around here. It might be disturbed away from it, but then it will quickly jump back to it. But when there's critical slowing down, then if it's disturbed away, it tends to linger around here, and it takes a long time to come back. So it can spend a lot of its time well away from the equilibrium point. And so if we look at the values of x, there will be a much greater range, much greater variance. It can be out here quite often, and it's not all just concentrated at the stable point. So that is another way to detect critical slowing down. Look at the variance in your data. And if you're finding that the variance increases, then it suggests you're getting close to a critical point. And lastly, let's have a look at that for the Rome data again. Okay, so this shows the variance in our Rome data set on civil disturbances. And to find the variance, we've got to have a number of values. So what it's doing is taking the last 10 values, which covers then a range of 250 years at 25 years a data point. So it takes the last 250 years of values, or the last 10 data points, and finds their variance. And so we have to start at 300, so because it goes back to 600, but then from then on we find a fairly low variance, and then it increases, and then it decays back down again. Then there's a peak there and another peak there. And we could argue that these are related to events in Roman history, so that this round about here is the Emperor Augustus taking power as the first emperor. So it's a transition from the Roman Republic to the Empire, and or the Principate. And round about here is the Emperor Diocletian, reorganizing the empire after a period of long period of disturbances. And then here is the fall of the Western Empire, traditionally 476. So we said that the variance, an increase in the variance, is associated with critical slowing down, a criticality, an approach to a critical transition. And indeed here we can see that the increase in the variance, the peaks in the variance, are somehow related to critical transitions. Now what we're plotting here, we need to be clear, is variance. It's not the amount of disturbance, it's the variance in the disturbance. So here the variance is low, but the amount of disturbance could in principle be quite high, but it just is staying the same over time. So you're at a stable, you might be at a stable point which has a high level of disturbance, but it's a stable point. You'll keep coming back to that high level of disturbance. If the system becomes a bit more peaceful, it switches back quickly to being back at that high level of disturbance. So that your it may mean that your society is completely chaotic, disorderly, warlike, etc. But that's not what we're talking about. We're talking about at the point of a transition. Are you transitioning to some other kind of behavior? So it might be that you're transitioning from this fixed point of are high levels of disturbance to a much more peaceful situation. So this is what this could represent. Here, the Rome was kind of locked in to a syndrome of having high levels of disturbance. But then we see the variance increasing. That shows we're getting towards this transition where it moves to an imperial system and it becomes much more orderly. But what we're picking up here is that there's some change in the system's behavior. There is a transition. Again, Diocletian was actually taking the empire from a disorderly condition to a more peaceful one, a more orderly one anyway. And so again, this rise in the variance is a rise in the variance in the level of disturbance, not a rise in the level of disturbance itself.